Hi and welcome back. So in this video we're going to be implementing the valid anagram problem. So let's get started. Let's see how we can do it. So in this video we're going to be implementing the linear time solution or the hash table solution in two ways. So one possible way we're going to show is the unordered int or unordered set, and basically we're going or unordered map, excuse me, which is basically an implementation of a hash map in C++. The other method we're going to show is using a normal vector to simulate the usage of a hash table. So let's try first to do the unordered map one, which is the usual hash map method, and then we're going to use the normal vector method. We're going to show the normal vector method. So let's get started. So we said we're going to need an unordered map or a hash map of char, a letter, to an integer, because each letter is going to be mapped into the number of times it's mapped. And then I go, okay, I go over all the elements in S, and then I basically say, okay, HSI plus plus. And then I go over all the letters in T, again, same from the pseudocode. And I do H or HTI minus minus. And then I go, okay, I want to check all the elements in H. So I go for auto element in H. If element dot second, which is the count, is not equal to 0, then we return a false. So we're looping over all the elements in H. If the element is not 0, then we return false. And then if we passed all these loops, then we simply return true. So let's first check if the code runs or not. And it runs, no problem. Let's try submitting the solution. And we got an accepted solution. So let's check. So our solution performs pretty nicely. It's 41%, it's in the linear time area. So let's now try and do the normal vector hash map here. So usually, if we think about all the letters, right, any letter from 0, 1, 2 can be represented in ASCII. So if you're not familiar with ASCII, just pause the video for a minute, go search it on Wikipedia. It shouldn't take more than a few seconds or minutes to read. It's an easy concept, but basically we can think that A, B, all these letters are basically stored as an integer value, or as an integer value basically. So each letter actually corresponds. For example, the letter A, capital A, corresponds to the letter 65, to the number 65. So one possible, and we know that ASCII values range between, they're less than 128, they're from 0, and they're bigger than 0. So they're from 0 to 127. So let's try and get an idea for that. So instead of storing the actual letters, why don't we generate, so let's delete this code for now. Why don't we generate a vector that carries only integer values, call it H, but this time we're going to make its size 128, and it's going to store 0 for all the values. So in other words, we're making our hash table is actually made of all the possible letters, because all the possible letters, whether they're A, B, C, even a capital A, capital B, any letter basically, or any character, can be expressed as an ASCII. So if we know that, then any letter is already mapped to an integer. So I can just use that integer as an index of H to access the count of that letter. So if I do, for example, HA, then that means I'm accessing the 65th index. So I can do HA++, which would exactly match as if I'm doing H65++. So in other words, instead of just storing the letters that are in S or T, I can just make a table, a hash table of size 128, which is gonna store all the letters, and do the same algorithm again. So let's go again. We go through all the letters, and this time we do HSI++, same as last time, and then we do the same thing. Let's just copy that code, maybe make things a little faster. So we copy this code here, but instead we do TI and change this to T and this to minus minus. Finally, we're gonna go through all the elements in the hash table, and there are 128 of them. So we go I less than 128, and then if HI is not equal to 0, then we return false, just as last time, else we return true. If all of them are zeros, then we return true. So let's try running the code, see if we have any problems first. We don't, and then we submit the solution. Hopefully it should be accepted just like this solution was. And yeah, it was. Performance-wise, it performs actually better than the hash table, and the reason for that is the hash table, if you think about it, let's go back to the code. If you think about it, the hash table in C++ has inside of it has a hash function, and this hash function actually takes, it still takes linear time, but in terms of the absolute number of operations that are done, it consumes quite a number of numbers. So what I'm actually doing when I had the hash table, the unordered map H, or char to int H, when I did this operation, there was actually some extra operations which were being done here to hash SI, even though it's just a letter, but it's still a hash function. We still have a hash function for that. And that is why actually this solution with just an H performs much better, because the hash table is fixed. Our hash function is exactly, if you think about it, the hash function h of I is equal to I. It's exactly that. We take a letter, or not exactly I, but ASCII, the ASCII value of I. So for a letter I, the hash function is the ASCII value of I. I take A and I map it to, or A, capital A, and I map it to 65, which is the ASCII value of I. But this is already done in the language itself. So our hash function is quite fast, and this is why this solution performs slightly better than the other solution. So yeah, I just wanted to show you two different possible implementations. It's not always possible to do this sort of trick, and the reason for that is, suppose we were doing, instead of letters, we were doing strings. So the space of strings is actually quite big, so we would need an unordered map. But I thought it was quite interesting just to show you one other way other than unordered map that we can sort of use here to also solve the problem. So yeah, thank you for watching the video. Until the next time, happy coding.